We present 3D Highlighter, localizing regions on 3D shapes via text descriptions. Where would you put a necklace on a horse? How about headlights on a UFO or shoes on an alien? More generally, can we localize arbitrary text-specified regions on 3D shapes? In this work, we present a method to do exactly this. 3D Highlighter localizes semantic regions on a shape using text as input. Our technique reasons about where to place seemingly unrelated concepts in semantically meaningful locations on the 3D shape. For example, our method can hallucinate how to place a poncho on a horse or headphones on a bunny. Please see our project page for more information. Our work is motivated by the importance of semantic region localization for 3D modeling and editing, as many of these tasks need to be applied locally. As an example, if we have a texture that we only want to apply to a specific semantic region, determining the vertices and faces over which to apply it would be a tedious and manual task. With localizations produced by 3D Highlighter, we can automate this entire process. Thus, our method opens up many possibilities for semantically aware processing of 3D shapes. This localization task is challenging for many reasons. First, we do not have any 3D labels or 3D datasets for this task, and thus we do not use any 3D supervision. Previous work relies on 3D data, which constrains them to specific shapes and categories present in the training data. Our objective is to localize any region described by open vocabulary using information about only a single shape, a task for which 3D data does not exist. We are interested in analyzing arbitrary meshes in the wild, and thus our method must robustly work on low-quality meshes that might be non-manifold, contain boundaries, or have self-intersections. Another challenge is that many of the localizations are ill-defined. For example, since candles do not wear hats, in order to localize a hat on a candle, our method must hallucinate a plausible localization on an out-of-distribution mesh and prompt combination. The key idea behind our method is the concept of analysis via synthesis, the process of extracting analytic information implicitly contained in the generative process. Our inspiration originates from text-to-mesh, which styles a mesh by optimizing its color and texture. We observe that these stylizations display global consistency and semantic awareness. However, text-to-mesh just creates the style and does not give us explicit information about the underlying semantics. This begs the question: how can we formulate our problem to explicitly extract these semantic properties? Our method accomplishes this by framing our analytical problem of region localization as a generative problem. Instead of simply styling a mesh by directly predicting colors, we force a neural field to predict the localization. Then we can use this predicted localization to determine the vertex colors. The core component of our method is our neural highlighter. This coordinate network takes in a vertex and predicts a probability corresponding to that vertex's membership to the localization region. This network gives us an explicit segmentation of the vertices. The question now is how to utilize this segmentation information to synthesize colors per vertex so that we can optimize our network. We compute the style of each vertex using a probability-weighted blend of predefined colors. This vertex coloring procedure is entirely dependent on the predicted probabilities and will produce better stylizations when the probabilities are more accurate and decisive. Formulating this as a synthesis task enables us to leverage similar optimization techniques as generative methods. Starting with an input mesh, we pass all vertices through our neural highlighter and blending module to get an initial guess of the estimated highlight. Next, we render 2D images of our highlighted mesh with a differentiable renderer. Then, we utilize the joint image text embedding space of CLIP, a 2D pre-trained vision language model. We encode each render with CLIP's image encoder and take their average latent representation. Similarly, We encode our target text prompt with CLIP's text encoder to get a second encoding in the same latent space. Finally, we compute the similarity of our two latent representations and use this loss to update the weights of our neural highlighter. Here we show results of 3D highlighter on many diverse mesh and prompt combinations. Our approach is able to obtain semantic localizations on multiple object classes, such as animals, household objects, and more. Furthermore, many of these target localizations are unrelated to the mesh they are being localized on. For example, lamps don't wear necklaces, and pumpkins don't have wings. 3D highlighter is able to localize different regions on the same mesh. On this bunny, our method is able to produce distinct localizations that reflect the nuanced differences between headphones and hat. Now, taking a look at this dog mesh, we observe that the geometry of the waist and neck are very similar. When tasked with localizing both belt and necklace, our method places them in different locations. Since the geometry of these two locations is so similar, this result demonstrates global semantic understanding, as the network cannot rely solely on the local geometry. 3D highlighter's ability to localize semantic regions allows for many applications in geometry processing. Once we localize a region with our method, we can apply a predefined color and texture to only that region. We can also compute the localization of multiple regions and use those localizations to composite different styles together on a single mesh. In addition to stylization, 3D highlighter can also be used to perform geometric edits. Once we have localized a region, we can manipulate the geometry of the mesh with operations such as stretching or extrusion. To summarize, our method utilizes CLIP, a pre-trained 2D model, and thus requires no 3D supervision or 3D datasets. Our method allows for intuitive control over the localization region using text. Our method learns a neural field over the vertex input space and thus is able to work on various meshes regardless of their quality. Finally, our method uses synthesis as a means for extracting the underlying analysis. The question going forward is, what other properties can we infer via synthesis? If we are able to extract localizations here, what else can we extract? Our paper and code are publicly available at the following link. Thanks for listening.